what I want to do now is actually talk a little bit about the system itself here and about the design of the system and explain what's actually happening here and why it's designed this way, and again, my focus on expression. So this is, as I mentioned, this is the Buchla 200U. This is a current electronic music instrument that is still being made now by Buchla. Don Buchla, again, was a contemporary, or is a contemporary, of Bob Moog, and he took a very different path than Moog did. And one of the reasons I think that Moog's instruments became so popular, of course the Mini Moog was like the first real breakout electronic music synthesizer, was that Moog's instruments had keyboards on them. They had black and white keyboards. And you could use them to play, you know, you could play rock and roll with them basically, because you could plug them into a really loud amplifier and it could be louder than a guitar. And it could be a bass, you know, it could be louder than a bass and all that sort of stuff. And of course, a lot of wonderful music was made with that instrument. Buchla always resisted the idea of the black and white keyboard because his particular interest was not towards tonal music, but towards timbral control. And his modules were really about making new sounds, not essentially making, playing melodies with different kinds of sounds, but actually making new music that were based on new sounds. So he he only had a couple instruments in his entire history that had actual black and white keyboards on. He always, from the beginning, would try to work with alternate methods of control that would still allow for direct expressive control, but that weren't black and white oriented, weren't chromatically oriented in that sense. So a lot of his early instruments had touch plates on them that were capacitive touch plates that were sensitive to pressure, but also position and so forth. And those were actually some of the very first precursors to this particular instrument and other instruments like this now. But again, his idea was to get as wide a variety of timbre as possible, in addition to having all those other levels of control. So he made sequencers like this thing, but his oscillators in particular are always dual oscillators. There's always two of them in a package. So every one of these oscillators that I have here, I have 5 oscillators in this system, 5 oscillator modules, but each of those is a dual oscillator. So in fact, there are 10 oscillators in this system. And each of those oscillators are designed to modulate each other, so you can do cross-modulation. Are you familiar with cross-modulation? Do you guys know what cross-modulation is? Where you take 2 oscillators and modulate them with each other, frequency or amplitude modulating with each other. You get very complex and not always predictable sounds that way. It's a way to set up a kind of a chaotic feedback system in a sense, in a single, with actually very limited resources, let's put it that way. So his oscillators are designed to be able to be used independently, but they're really designed to be used together to make something that produces very complex timbres. And the same with his filters. His filters are filters that are his VCAs, his voltage control amplifiers that control amplitude, also have filters in them. So he's able to have, see if I add up all the filters here, I have 4, 8, 14. And because I have 2 triple filters that are actually individual bandpass filters, but every one of the VCAs also has a low pass filter. So there's a lot of filtering in there. You can start out with very complex waveforms and further process those with lots of complex levels of filtering. And he also was very interested in the idea of random control, of introducing randomness into timbre control, amplitude control, and so forth. So one of his very early modules was called the source of uncertainty. And it was a white noise generator, of course, and a white noise generator generates every frequency and every amplitude in the audible spectrum with random distribution. And it's a great source to not only generate random sound, but also random control. If you filter that and process it so that you're extracting the amplitudes of those randomly generated waveforms, you can generate random voltage control. And that's what this one does. This has both pink and blue and white noise, but it also has sample and hold generators that are continuous sample and hold, but also discrete. And you can weight those so that you can distribute that randomness within a narrower band or a wider band. You can also randomly store random voltages and randomly play them back. So that has a lot of complexity built into that one module. And again, that was designed to not necessarily generate a lot of random boops and beeps as such, although of course you did a lot back then, but the ability to have unpredictability, essentially, and unpredictability on many levels. It didn't have to be necessarily random boops and beeps, but you could set up systems whereby the timbre was changing randomly or rather, the timbre was changing unpredictably in a manner that was really much more organic than your typical oscillator, which is pumping out a square wave or a sawtooth or something like that never changes. So his systems were always designed with the idea of, again, multiple levels of control, but also great high density of the modules themselves, and of the ability to introduce unpredictability or instability in a controllable way, sort of controlled, unpredictability in a sense, into the system itself. So by itself, this is actually a complex synthesizer. It has a lot of sound sources. As I said, it's got 10 oscillators. It has 4 dual analog oscillators and 1 digital wavetable oscillator, and 2 sets of VCAs, so I can directly control the amplitude of up to 8 different sources, and also those VCAs have low-pass filters in them, so those are called low-pass gates. And then there are 2 triple bandpass filters that can be individually operated, but also can be sequenced together. There's a little sequencer built into those things, essentially. You can chain them together to make sequences of control, sequences of timbre control of the filter, but also, in fact, the filters themselves, the filter modules can be chained together. So you could have a six channel sequenced bandpass filter in which the bandwidth, the Q, and the amplitude and the center frequency are all individually controlled. And that's in one module by itself, basically. So each of these modules, some of these modules have their own little sequencers built into them, essentially. This sequencer here, which is called the 250E, which is this sequencer you saw me use a little bit there, the reason it's designed in this kind of circular format is so that it's really optimized for performance. You have 2 rows of knobs. There's a larger row outside, a smaller row inside. That each of those, the outside row, the outside ring, controls 2 different independent sequencer stages. And the inside ring can be a 3rd independent stage, or you can apply that to the timing of each individual step. And those can be quantized so that you can quantize those to pitches, or you can quantize those to even multiples or divisions of your basic pulse, so that you can keep things in time as you're playing with it. It's a very powerful sequencer, and it has, as I said, independent stages, independent trigger outs, all kinds of things that you can do in terms of having the thing control itself or be controlled from outside stages. You can randomly access the stages. You can randomly step through presets in the thing. I'll talk about presets in a sec, but essentially this is actually a very complex sequencer. Not something that you're going to necessarily sequence a song on because it's basically 16 steps, but something that you set up a basic set of parameters and then you can perform with that. And again, we're talking about something that is a higher level of control than simply playing those notes. You can play multiple streams of notes and control both the timing and the pitching and gating of those notes independently. And so something like this is, again, a good exemplar of something that gives you these multiple levels of control. You have direct control of pitch, but you also have higher levels of control. So that's essentially the system. Now there are 3 things that I haven't mentioned here that are significant. This module over here, this big one, is kind of the master output module, and that's a mixer, a multiple stage mixer that also has built-in quad panning on 4 independent channels. And you can see that there's, if you look closely, you can see that there's a set of yellow LEDs that are kind of moving around in circles. Each of those is an independent 4-channel panner. And you can control that, quad panning with voltage control if you want. It also has its own speed controls. There is what they call the swirl control, which lets you control what shall I say, the diffusion of the distribution of those 4 channels, but also the direction of that swirl, so to speak. So you can set it so that if we had 4 speakers here, we can set it so that at the maximum external swirl, so to speak, the sound is heard only individually in each of the 4 speakers as it moves around. But it can also sort of contract in, and the mix can be controlled in such a way that you can have it moving more towards the center of the space, essentially. And as I said, it can move independently in either direction, and that happens independently for each of 4 channels. So the way I have this set up, in fact, is that I have 4 independent voices, each of which is going into one of those channels, so that as I'm playing, and coincidentally, this is, again, it's kind of a 4-voice system, each of those 4 voices is independently moving in the quad space. And when I combine that with the quad processor, the quad reverb processor, I have really very powerful control over the size and shaping of the space and the movement of those voices within the space. Because one of the things that this does, this core control, is that there's a plug-in that's running in main stage that communicates with the reverb processor that lets me control all the parameters of the reverb, the room size, the mix, the front and back mix, the RT60, all these sort of reverb terms essentially that control the length of the reverb tail and also the size of the space, the virtual space in which this is happening, and things like pre-delay and post-delay and so forth. So it's quite a complex spatial processing system as well. And the spatial processing becomes another aspect of the expression, the fact that you can very precisely position things in space if you choose, or you can let the system do that and sort of get a very rich sonic spatial environment that way. That I hope that we'll be able to hear tomorrow when I play this in quad, in fact. So, and that's essentially what this big module here does. That's one of the reasons that it's so large and complex and expensive, is that it's doing a lot. There's a lot going on in there. So the other significant part of this, and the thing that makes this instrument really head and shoulders above most other modular systems. Modular systems, as you know, are connected by patchwords. Essentially, you create sounds by connecting the functions of the modules together with patchwords and setting up a signal chain. And your standard signal chain is you have an oscillator that goes into a filter, that goes into a VCA, that then goes out. And you control the pitch of the oscillator and maybe the timbre of the oscillator with some voltage control. You control the opening and closing of the filter and maybe the resonance of the filter with voltage control. And the shaping of the amplitude typically is done either directly with a knob or with a device, a control device, or with an envelope generator. And you trigger the envelope generator and it changes the shape of the amplitude over time to give you sounds that could simulate acoustic sounds, for example, which is really the original reason for the envelope generators, to give you a kind of a complex shape that mimicked the sound of acoustic instruments. The attack, decay, sustain, release, if you're familiar with that. So the thing about those systems, though, both the old systems and current analog modular systems. And as an aside, I'll say that it's really, it's kind of gratifying, but also surprising that there's been such a resurgence in analog synthesis lately. There are more manufacturers of analog modular synthesizers now than there were back in the heyday of those instruments. And some will do complete systems, like a company like Doepfer, for example, that has like 150 modules in their product line, or analog solutions or analog systems. Or there are sort of more boutique manufacturers that make individual modules that conform to one of the various standards that have developed over time. But gathered all together, there are probably 20 or more of those manufacturers, and there were only maybe 5 or 6 in the old days. So it's really kind of interesting that there's been such a revival. But in terms of performance, one of the real limitations of those systems is that they have no way to recall. They have no patch memory. And patch memory is an important thing, actually, and one of the reasons that MIDI took over from those systems back in, back beginning in the 80s, was that you could remember a setting. you could remember instead of having to write down the knob positions and where the patch cords went, and then hope that you could get that back again. And in the CEMS system I showed you, basically, when you were doing a piece of music, you set up the patch, you recorded it, you stripped it down, you maybe did other sounds and so forth, and you could never get back to the original sound again. You recorded it because you could never get it back, and unless it was the most simple kind of sound. But essentially any kind of complex system, simply because there was so much variability in the analog hardware itself, because the knobs weren't that precise and all that sort of thing, it was essentially impossible to reproduce something that you had done before. Certainly to reproduce it exactly. And it was also really hard to get those things in tune because they were very temperature sensitive. You know, you could spend all day getting the thing in tune, and somebody would open the door in the studio and it would go out of tune. So very typically, when I was doing the pieces that I was doing back then, many of which were drone pieces that were actually very precisely tuned, I'd have to set the thing up in the evening and let it just sort of sit there all night, stabilizing until the thing would get in tune, and then do the recording in the morning. Hoping, you know, that the temperature wouldn't change that much, just to be able to get the thing stay in tune for, you know, half an hour or something like that. So that again was a very, you know, it was a real drawback to those systems in that it made it very difficult to use those for performance. If you set up a patch and then you worked within the variations of that patch, you could do something. But if you wanted to have abrupt changes of timbre and so forth, that was very difficult to do. Buchla has realized that, and he's gotten around that by including patch memory in this. And so every one of these modules can actually remember up to 30 different presets. And those presets are managed with the preset manager. And what that means is that every knob on here, there's some that don't do it, but every knob has got a blue top, essentially, can have its position recalled as part of the patch itself. And that includes whatever that might be, the settings of the sequencer, the tuning of the oscillators, the timbres, and so forth. And there are also some other things. There's some internal routing in terms of, say, modulating one oscillator with another, but it can also be recalled as part of the preset. And that's managed through the preset manager. So you can recall up to 30 different presets that will recall every one of those knob positions, every one of the blue knob positions, instantly. So that, for example, when there's a patch here, this particular patch, for example, take this down, take that down. Here's one that has some fairly simple FM modulation on 4 different voices between a set of different sine waves. The sound you heard me play there before at one point in the performance. Because it's an FM sound, because it's not tuned, those pitches are not in tune. But right next door to that, there's one in which the pitches all are in tune. And then you can instantly switch between just different presets that I'm stepping through there, essentially. So I have the ability to remember the positioning of all these different knobs, including the tuning of the oscillators, the routing of the oscillators, and so forth. Now, the preset is not able to remember or restore the physical position of the patch cords. There's not little hands that reach out there. You know, that would be nice, but it doesn't do that. But there is a sort of limited way to do that, and that's what this module does over here, which is it's a 5x8 matrix switcher for both voltage control and for audio. And by routing a lot of the audio and control voltages through this, you can repatch things to a certain extent. So it has, as I said, 8 inputs and 5 outputs. So any 8 inputs can go to any 5 outputs in any combination. And you can actually mix those together too. It's not just a simple switcher, it's actually a matrix mixer. So by designing your patches in such a way that you can repatch it by way of the matrix mixer, and you can see as I'm stepping through some of these patches here, you see that the position of the LEDs on the matrix there is determining where things are going in what proportions and how many. So that's a more complex one. There are some here that are less complex. But you can see that I'm routing different things to different locations in different proportions depending on the patch itself. And again, that's really just sort of repatching stuff on the fly, basically. And so by combining that with your patch memory, you're able to get a very wide range of timbres and very wide range of control with a single patch. And in fact, that's what I've been doing. This patch here is the one I've been working with for the last 3 years or so. And just, in fact, making it more complex, increasing the density of the patch, but working with essentially one patch with many different presets and many different levels of control. Now, the other aspect of this whole thing that I haven't talked about yet is the continuum. And the continuum is what really makes this whole thing, to my mind, an expressive instrument, the thing that allows me to really control this in a way that is really musically expressive. The continuum itself can send out MIDI information, although you have to have the right kind of synthesizer to plug it into, basically. But essentially, it can send out MIDI, but it also has another protocol it uses called I2C, which is a very data communication protocol that is very high resolution. So the I2C can be similar to MIDI, but it has a lot more steps in it, essentially. It's a higher resolution thing. So this is communicating with this other device over here in the rack that has this bundle of cables coming out of it. It's called the CVC, the Continuum Voltage Converter. And what that does is take I2C signal from the continuum, and again, that's the position of 4 fingers with X, Y, Z data coming from those 4 fingers, and splits those out into individual channels of voltage control that I have routed to a bunch of different locations on here. And again, because I have the patch matrix involved, I can actually reroute those control voltages that are coming from the finger control to different purposes. So in most cases, the finger, say the y-axis is opening and closing a filter, the y-axis is doing timbre. But in some patches I have it set so that rather than controlling the filter, it's controlling the wave shape of the principal oscillator. And there's a lot of complex wave shaping that's available in the oscillator itself. So you can have timbre control, kind of intimate timbre control that's not really the same, nowhere near the same as opening and closing a filter, but where you're changing the harmonic structure of the waveform in a much more complex way than simply, adding and subtracting harmonics in order. The same way I have the amplitude is directly controlled with pressure, but I also have that controlling things like the modulation depth of the modulation oscillator when it is set to control to modulate some other function in the principal oscillator. So there, for example, where I have more complex sounds, like this one, for example. I think it's this one here. Where in that sound, the amplitude is also, the pressure is not only making the sound louder and softer, but it's also increasing the harmonic complexity of the sound by the fact that it's changing the amount of modulation that is changing what's called the modulation index between the modulating oscillator and the principal oscillator. So there's a lot that can be done with even those simple controls. So let me talk about the continuum a little bit. The continuum is invented by Lippold-Haken, and there have been, again, from the beginning of electronic music, there have been many attempts to make expressive controller instruments that are able to give you continuous control, but also precise continuous control. Now, the problem, of course, with the theremin, as we mentioned, is that you have the ability to very easily get continuous control, but it's very difficult to do precise control. With a keyboard, like a piano, for example, you have very precise control over pitch, but no control over the expression of that pitch at all. Once you initiate the pitch, there's nothing you can do really to change that pitch. You can't add vibrato or anything like that, the way you can with a violin, for example, or a wind instrument, where you have a direct, intimate, either breath control or fingertip control over the pitch itself. And one of my beliefs is that one of the real keys to expression is being able to have very precise control of pitch. Not simply to be able to hit a pitch in tune, which is important if you're playing tonal music, certainly, but also to be able to very subtly manipulate that pitch the way that you can with your voice, again, which is really the most expressive instrument there is. So the problem has always been how to be able to continuously control things and precisely control things in steps at the same time, which are really, essentially mutually exclusive concepts. So there have been many different attempts to do that. The ring string thing that Maurice Martineau came up with was a good step, but again, it had some limitations, primarily in that you couldn't play anything polyphonically, for one thing. That string metaphor doesn't work with multiple fingers. So there have been many attempts, and I think that this one, the continuum, is really among the most successful, possibly the most successful right now. It's a complex instrument, and it's mechanically and both mechanically and in terms of programming very complex. But right now, I don't think that there's anything else out there that really has the expression that this does. So how it works is that there is a neoprene surface, and when we're done, you can all play this a little bit to see how it works. There's a neoprene surface, neoprene being the same stuff that dive suits are made out of, so it's kind of squashy. And that's about maybe a 1/4 inch thick or so. Underneath there, ranging this way, are about 128 steel rods. And those steel rods are, I would guess they're about 3/16 of an inch thick, something like that. Maybe even less. They're about this long. So they kind of run the width of the instrument here. At the end of each of those rods is a little spring. There's a little hole drilled in that thing. And there's a tiny little spring, it's about 1/4 of an inch long, that then sits in a socket on each end of those, so that each of those steel rods is spring mounted and is essentially floating independently. At the end of each of those rods, at each end of every one of those rods is a little magnet. And that magnet is moving in a magnetic field. And the movement of that magnet is where that information is being derived from. So that if I press down in the center, for example, of this virtual key here, multiple rods are being pushed down. And because it's being pushed in the center, the sensing system under here, which is called a Hall effect sensor, for those of you who know about such things, the sensing system underneath here knows that the rod is being pushed down evenly because both ends are going down more or less the same. So it knows that it's being pressed down from the center. If I press it up here, that end goes down more than this end, so it knows that it's that end, and so forth. So it's able to determine not only the fact that it's being pressed down, but where along the length of that rod it's being pressed down. And that's how it derives the Y information. So the Z information, the actual pressure, is derived from the up and down motion of the rods, and the Y is derived from the sort of the rocking of the rods, as it were. Because there are multiple rods under each finger, when you press it down, several rods go down, 3 or 4 rods at a time go down. And because your finger isn't pressing down quite as evenly on all of those rods, it's able to sense that as well, and that's where it derives the x-axis information, like the pitch information, for example. So the pitch information is, or again, I should say the x-axis information. Normally, or very often when you're using this, it's x is pitch, z is amplitude, and y is timbre. It doesn't have to be that way, of course, but that's a very conventional way to do it, and that's how I use it almost all the time. And there are, well, we'll get to that in a bit, but essentially the pitch information, it knows that it's able to differentiate between those rods and is able to generate pitch information from that. So let me get a very, very straightforward sound here. Take that down. Turn that off. Okay. So it's able to, so I have it set so that the amplitude is directly under fingertip control. I'm not actually using envelope generators for this. There are triggers that you can trigger out from this that can be generating envelopes, but I find it to be much more expressive to use direct fingertip envelopes. Because an envelope essentially, unless you have voltage control over each of those stages, an envelope tends not to change. It tends to be the same every time, unless you reprogram it. So if you have it set so it has a sharp attack and a long decay, there's not a lot you can do to change that unless you send a voltage in to change the length of the attack or something like that. But if you're triggering that from a keyboard, the envelope is pretty much always going to be the same. There's a sustain component, there might be velocity and so forth involved, but essentially that actual shape is going to be roughly the same. Here you have direct control over that shape. I can have, I'll even take off the reverb here completely. I can make a very percussive sound that way, just by tapping it, so I get a very sharp attack and decay. I can have a long attack and a sharp decay, or vice versa. And once it's attacked, I can control the amplitude directly, so I can do tremolos and things like that. And it is very sensitive that way. Now, that's independent of the x-axis thing, and so I'm able to control pitch directly. And because I'm sending out continuous control from this, I can continuously control that pitch. So I can do glissandos, and it also senses, I can do very expressive finger vibrato, and I can do that for up to 4 voices independently, because once your finger is down, the sensing system will track that. So I can each of those inner voices can be independently changed. And if I had sufficient, I'm working on it, but if I had sufficient control, I could actually do independent timbre and amplitude control of each of those voices, even the inner voices. And that's something that no other instrument can really do, you know. And as I said, if you use this either with the internal sounds, which I'll get to in a sec, or through MIDI, you can control up to 16 voices. I mean, you've only got 10 fingers, but you know, you can do, if you had somebody helping you, for example. But it'll easily do 10. So that it's just wonderfully expressive, wonderfully complex. It's an expensive instrument and all that sort of thing, but it's handmade. It's like a watch in there. And in fact, I'll tell you why I know that. And this is really like just one of the worst things that ever happened to me, just about, or it could have been, at least. Let me put it that way. The reason I got to know this instrument was that there's a musician I work with named Jordan Rudess, who's the keyboard player in a band called Dream Theater, who's a well-known Prague virtuoso. And most of you, I guess, know him. You've seen him. He's my next-door neighbor, in fact. And when we moved into our house, in fact, the real estate agent said, "Oh, you're a musician. You know, there's a musician next door." I said, "Oh, yeah. What's his name?" Jordan Rudess. He plays with a band called Dream Theater. I said, "Oh, that's great. I never heard of Dream Theater." But I think I've heard of him. Maybe he didn't used to like program sounds for chord or something like that. So I guess he plays okay or something. So eventually, I got to be good friends with him, and we've done some playing together and so forth. And he is, in addition to being an incredible virtuoso, I mean, he attended Juilliard when he was 7, right, and was there for 10 years. No, I think 11 years, actually. He's studying strictly classical piano. But one day somebody showed him a mini mode, and he went completely nuts over that, because among he, like me, actually, was always liked the idea of being able to have a keyboard instrument that you could control timbre on, that you could do different sounds, that was able to be more expressive than what the piano could do. You can do a lot with the piano. I mean, the piano is a wonderful instrument, but it really is, there's very little expressive control you can do with it once you hit a note. And he really loved the idea of just being able to play a note and like twist a knob, and all these harmonics would spray out and that sort of stuff. He just completely fell in love with it. And so he's been very heavily invested in electronic music technology since then, and is really very well known for, oh, thank you, Carolyn, pointing that out. There's a DVD I have as part of my merchandise, which is a live concert that I did with Jordan. He's also been very heavily involved in music technology. He has like a number of iPhone apps, for example, that are performance instruments that are based. His main one is this thing called MorphWiz, which has won a bunch of awards and things like that. That is actually based on the idea of the continuum. So a few years ago, and I also have done a lot of technical work for Jordan. I work on his computers and that kind of thing. So it's been a nice relationship that way. And a few years ago, he said, I really would like to have something that's like a fretless keyboard. I really want something that I can play the way that a fretless bass can play, with that sort of expression, but still have some sort of precision, There are all kinds of ribbon controllers that you can get and so forth, but they have sort of the same problem that the theremin does, that it's hard to do precise pitch control. So I said, well, you know, maybe there's something that we could do with FSRs. He knew some Korean engineers that might be able to do something. So we started looking into it, and in the course of doing so, I came across the continuum, and I said, Jordan, just get this thing, you know. This guy's already done this. We can never do anything as good as this. Why don't we just get this thing? So he did. He contacted Lippold. He bought one. Lippold, you know, is one guy. He makes these things by hand. He doesn't give anybody breaks, you know. Chick Corea called him up and said, I want one of these. And said, okay, it's $2,500. He said, no, I want one for free. I said, no. No, I don't give them away. Lippold is in fact a doctor of physics at Champlain, Illinois. So he has a job, you know. He doesn't really have to worry about that stuff. This is his hobby. But he had invented this instrument, and so we got a hold of the thing, and I started playing. And this was actually before I got this instrument. I was working with the KEMA system a lot at the time, and this was really designed to integrate very well with the KEMA system. And I realized immediately that this was really an incredibly expressive instrument, control instrument. So Jordan got one. In fact, he got two, because he always has to have two when he goes on the road, because he has to have a backup. And I had played with it a bit, and I was working with Lippold to get one, essentially, but didn't have my own at the time. And Jordan went on the road with Dream Theater and was touring with the thing, and it gets banged around on the road, of course. And so when it came back off the road, it had something rattling around inside. And something had come loose, probably a nut. In fact, it was a nut, as it turns out. And he said, you know, I'm concerned about this thing rattling around in there. You know, it might short out a board or something. We called up Lippold. Lippold says, well, you know, you can send it to me and it'll be out of commission for a couple of weeks, or you can fix it yourself and I'll send you the instructions on how to fix it. I said, okay, I'll do that, you know. I can use a screwdriver and that sort of thing. So at the time, Lippold had some printed instructions, but they weren't actually, as it turns out, in the proper order. There is an order in which you have to do things with this. And if you don't do things in the right order, it's very bad. So I'm looking through the instructions, and the instructions start by telling you to take the top off. And in fact, what you need to do to fix this particular problem is take the bottom off. So I took the top off, and as it turns out, that the neoprene here is only held in by the top, and the rods are only held in by the neoprene. So you take the top off, and you take the neoprene, and all the rods just spring out. And that's what happens. So I got Jordan's thing, I took it apart. I'm up in my studio, which has a gray carpet similar to this, and I take it apart, and all these rods just fly out of this thing, because the springs are fairly tight. And the springs aren't actually attached to the rods, they're just in these holes, and the magnets hold them in. So all the springs came out. And this is there's like 200 of these things, right? And they go on the floor, and they immediately disappear in the carpet, because they're little gray things about this long, and it's in the gray carpet, right? And so it was one of those experiences where, you know, this was probably happened to you, whereby you do something that takes a second that you know is going to take 3 days for you to fix. And I almost threw up, honestly. I mean, it just destroyed this $5,000 instrument. It'll never work again. He's going to kill him. So, in fact, I was able to put it back together again. I found all but one of the springs, in fact. I put all the rods back in. It's devilishly difficult to do that, because the springs want to stick to the magnet. They don't want to go in the hole. So you have to it's unbelievable. The magnets are only held on by their magnetism. They're not actually attached, right? So the magnets want to come loose. They want to stick, the springs want to stick to the magnets. The whole thing wants to stick to the case, you know, instead of in its proper channel. And you got to do that 120 times. So you got to put in one, and then you got to take the neoprene and sort of hold it down with a book or something. Then you got to put the next one and hold it down. And then you got to do that, like I said, like 120 times. So it took about 2 days to put that thing back together again. So, but I got it back together again, and all but this one spring, which I kind of hid off on the end here. And it all worked, unbelievably. It all worked when I put it back together again. So I couldn't bring myself to call Lippold and tell him what I had done before I put it back together again. I thought I'd actually try to see what I could do. So I said, you know, I called up Lippold. I took the bottom off and found the loose nut, which took about, you know, 4 seconds or something like that. And I called up Lippold and said, Lippold, I did something bad. I kind of broke the instrument, but I was able to put it back together again. And he said, oh, well, I guess you're now the world's only qualified continuum field technician. and that was it. In fact, the thing worked. So in fact, I am the world's only qualified field technician. Because as far as I know, I'm the only person who's ever taken one apart besides him. But at any rate, that's why it's so expensive. People complain about the price of the thing, but it's built like a watch in there. You would not believe how complex it is. So originally, this was strictly a controller, but lately he has added a function here which lets it play some internal sounds. And those internal sounds are designed to really take advantage of the expression of the instrument. So by themselves, the sounds are not, well, some of them are actually fairly complex. So mostly they're physical modeling sounds. So there is one like this flute, for example, which has an overblow and so forth, but also has the ability to add some breath in depending on pressure and so forth. And this is really an incredibly expressive sound in and of itself. And there are a bunch of other sounds, basically simple oscillator sounds, that let you really take advantage of the expression of the instruments. And some of them are, like I said, they're physical modeling sounds, so some of them are blown pipes like that, some of them are plucked strings, some of them are, in fact, let me get a plucked string up here. Take the attack out depending on how you do it, but if you attack it sharply, you get that very noisy percussive attack sound that you get almost like from snapping a string against the fingerboard. And again, this is all just under finger control, and this is all polyphonic as well, and these are 16 voice instruments. So this is an incredibly expressive instrument just by itself. And combined with something like an analog synthesizer or with a properly programmed MIDI synthesizer. The thing about MIDI is that you need to, because you're sending pitch bend messages out, you need to be in what's called basically MIDI mono mode, where you have multiple channels, each of which has a single voice on it, so that you can channelize each of those pitch bend messages independently. So you need to have something a synthesizer that can do multi-timbral programming. But with that, you get something that is actually a very expressive control instrument. So let's see. Yeah, I think we'll leave it at that. What I'm going to do now, to close out my section of this at least, is I want to play you something that I think shows the expression of the instrument, of the system, really to advantage. And what I'm going to do is play a composition, or rather a section of a composition by Olivier Messiaen that is, this section by itself is called Oraison. And this is from a piece that Messiaen's a French composer who died just fairly recently. So he is a 20th century French composer who has a very interesting approach to harmony and to timbre and so forth. If you're familiar with his work, he uses a lot of birdsong and so forth as sources, and has, unlike many 20th century composers, isn't afraid of tonality. He likes dissonance, but he also likes tonality. So this particular piece here was originally written for the French Exposition of 1937, something like that, for an ensemble of 6 en martineau. And it was called, the original piece was called the Festival of the Beautiful Waters, or something like that. And for the exposition itself, it was there was a whole multimedia business going on. There were fountains and colored lights and fireworks and all that sort of stuff. And this was the music for that. And as far as I know, that was the first piece of music, the first piece of performance electronic music written exclusively for electronic instruments. So the very first purely electronic performance composition. It's in 6 sections, and some of them are designed to sort of imitate the fountains and so forth. But this particular section that I'm going to play, the original name of it was called Eau, or L'eau, which is just water in French. And confusingly, there are 3 different sections of that piece that all have the same name. And this particular part of it has been subsequently extracted and turned into kind of what, there's not a lot of repertoire for the Hallmark novel, but what there is, this is one of the standard repertoire pieces for that. And the other thing is that Messiaen used this piece as a section for his Quartet for the End of Time. And for those of you who are familiar with Messiaen and the Quartet for the End of Time, he composed that in a prisoner of war camp in 1941 in Germany, or in Silesia, where he had been captured. He was an ambulance driver in World War II. He'd been captured and was put into this, not a concentration camp, but a prisoner of war camp. But it still was no picnic, certainly. And he was allowed, the commander of the camp, who was apparently an aesthete of some sort, allowed him to work on music while he was there, and he wrote this piece of music for the available instruments, which were the instruments they had in the camp, and the people that they had available to play it, which was piano, violin, cello, and clarinet. And so the Quartet for the End of Time, he took one section of this other piece and repurposed it for cello and piano. And so the Quartet for the End of Time is one of the great classics of 20th century music, and something that is, to think of that being composed in the circumstances that it was composed, and that such a beautiful piece of music was a result, is really quite extraordinary. So what I want to do is play this piece for you, and then any questions you have, or if anybody just wants to play the instrument, you're welcome to do that. So this will take about 10 minutes or so. This is Orison by Olivier Messiaen from 1937. I've transcribed it, obviously. Set up my transposition here. Go ahead. We'll start over.
Sorry.
That's okay.
Got a lot of incidents here.
I understand.